Hello everyone and welcome to Calculus Grade 12 classes. And in today's class we're going to discuss certain problems that are going to involve vertical and horizontal asymptotes and functions. And as you may know, we already covered this in our lecture classes. You can check them out in our course material, in our PowerPoint slides, or in our lecture recordings. So today's class, I would like to start with outcomes, definitely. And outcomes are pretty straightforward. We're going to learn how to find vertical asymptotes and horizontal asymptotes. As well, we're going to practice problem solving involving both of those. Any questions so far?
No.
Perfect. So for now, I would like you to revise what we covered in our lecture. So, Alan,
Yeah.
would you mind to remind us, how do you understand vertical asymptotes of rational functions?
Vertical asymptote is a line, an imaginary line that a function cannot cross or touch.
Yes, that's absolutely right. And how do we define vertical asymptote for rational functions? It's one you can see on your screen, where we have function divided by another function. Sometimes these are two polynomial functions. And what property should be satisfied in order for vertical asymptote to exist?
Q of x should equal 0. It should if Q of C equals 0 and P of C does not equal 0.
Absolutely right. Or in other words, you can also understand it as limit definition, right? When we're talking about vertical asymptote, we say that the limit of this function as x travels to certain value c, certain arbitrary value, right? Our function that looks like p of x over q of x is gonna have a limit that equals infinity, right?
Yeah.
Basically, that's what vertical asymptote is. Because if you look on the graphing representation of vertical asymptotes, let's say for a certain graph, it's going to be positioned at x equals 2, for example, right? Just as an intuitive explanation, right? So we have x equals 2. At this point, we're going to have vertical asymptotes. Vertical means it looking upwards, basically, or has an angle of 90 degrees with x-axis. Am I correct?
Yeah.
So what's going to happen with function around and at this line? So definitely, our vertical asymptote will cause the line to a vertical asymptote will cause the function to travel to this asymptote, but never touch it or cross it. Am I right?
Yeah.
So basically, what we see here, if we have 0 in the denominator, function is not defined at the point, thus the limit is not defined. But for convenience, we call such limit infinity, because infinity is not a number, it's a symbol, right? Remember, infinity is just a symbol that describes attitude of a function.
Yeah.
Do you agree with me?
Yeah.
So what we see here, that when we have vertical asymptotes, around this vertical asymptotes, function would behave either like infinitely growing function or infinitely decreasing function.
Yeah.
Oh, sorry. Asymptotes to the left-hand side may look like this, and to the right-hand side, it may look like this. Like we coming from negative infinity, right? On the other hand, it can also look like this, like we're coming from positive infinity. That varies from case to case, and that's why we have to study limit to the left and right hand side from the vertical asymptote once we found it. And do you remember how we do that? We simply say that it's a limit of x traveling to c. If it's from the left-hand side, Yusuf, what sign would we have?
Negative.
Absolutely right. And if we're approaching from the right-hand side,
Positive.
absolutely correct. So do you recall it? Do you refresh your memory?
Yeah.
Yeah.
So please make sure you have this in your copybooks. I'm gonna give you a minute to write it down, okay? We're gonna need it in our practice. Let me know once you finish.
I have it already.
I got it down.
Perfect. Let's move on. In the next slide, what type of limit do you see here? Yusuf, can you explain me what this limit gives us? What type of information it gives us about graph?
It's a reciprocal function. And the limit is infinity. What else?
So you gotta recall that we have several funny properties of a graph, right? One of
Yeah.
them are critical points, such as local extrema. Do you recall those? When derivative of a function equals 0, we have a local, we have critical point, and it could be either local minima, local extrema, or neither. Am I right?
Yeah.
So you gotta link this knowledge to the other one that says if limit of a function is 0 as x travels to infinity, we're gonna get horizontal asymptote. It's basically limits at infinity are giving us horizontal asymptote. What this first limit tells us that as x x tends to positive infinity, do you recall that?
Yeah.
X tends to positive infinity, our function would approach value of 0 for this particular case.
Yeah.
When x tends to negative infinity, it's also going to result in 0. Does it make sense?
Yeah.
It's going to result in limit 0. So basically, when we travel into positive infinity, when x tends to be positive infinity, y value is going to try to reach y equals 0. Or in other words, it's going to be our horizontal asymptotes if you look on the graph. Do you
Okay.
see this?
Yeah.
This is exactly the line that function tends to reach, but would never do that. Because if you see, this function is undefined for x equals 0, right?
Yeah.
And this function never equals 0. So y would never equal 0 for this function. On the other hand, limit of this function could be 0 because limit by its nature, it's a study of a graph around the point or close to the point.
Yeah.
Am I right?
Yeah.
So in this case, you can remember if function in infinity travels to certain limit, then this limit is going to be the horizontal asymptote. This limit could be different from 0. This is just some random example that gives us vertical asymptotes equals 0.
Okay, yeah.
And you're gonna see examples when this horizontal asymptotes is not 0. For example, if instead of 1 over x, I had 1 over x plus 1, what would be my limiting value? If I know that I have limit x travels to positive infinity of the following function, right?
Yeah.
I know that this turns into 0 once I substitute x for infinity, right? So I'm gonna have 0 plus 1, which results in limit of this function 1.
Oh, okay, yeah.
And the same stuff is gonna happen to the x tends to negative infinity. And for this case, we would have exactly the same shape of a graph, but it's gonna be shifted upwards by 1. So we're gonna have horizontal asymptote, sorry, y equals 1. Does it make sense?
Yeah.
Alan?
Yeah.
Do you have any questions?
I don't
No.
have any questions now.
So, Yusuf, can you please read this definition? I would like you to memorize it as a rock solid because this is what you're gonna use a lot.
Horizontal asymptotes and limits at infinity. If limit x is infinity, fx equals L, or limits after the x equals L, we say that the line y equals L is horizontal asymptote of the line of the graph of fx.
So, basically what we just discussed together. Any questions?
I'm just writing it down.
Perfect, take your time.
Yeah, just 1 second. I got it.
Yeah, you got it.
Perfect, let's move on. And here's basically a summary of unit 4.3. I want you guys to go through it in next few minutes and we discuss it together, okay? And I want you to ask any question if you don't understand it.
Okay.
So take a minute. So do you need more time, guys?
No, I understand it.
So
So
basically, the algorithm outlines like the steps for sketching a curve.
pardon?
The algorithm outlines the steps for sketching a curves, and it includes like checking for discontinuities and determining the vertical asymptotes and like finding the intercepts and critical points.
Yes, basically, we already know that curved sketch can be plotted by using only 3 points, right?
Yeah,
As you did it with parabola. And in fact, all curved sketches consist of intervals at which they are increasing or decreasing. And for us, it's sufficient to know 1 point on an interval and how function behaves in this interval in order to plot it. Because if we already can identify critical points, we can find local minima, local extrema. Then we can find how function acts to the left and right hand side from those points. Same approach we can implement when working with vertical and horizontal asymptotes. We're finding those asymptotes, we're defining how function acts around those asymptotes. So when we find that limit of a function when x tends to be some arbitrary number travels to infinity or positive or negative, we already know what y value are going to be around this asymptote, right? For horizontal asymptotes, on the other hand, if we know that x travels to infinity, then it doesn't matter which side, and we find the limit of such function, we already can start plotting those asymptotes and plotting our graph around those asymptotes. Is that clear?
yeah, that's clear.
So make sure you understand that our function can have a limit, positive as well as negative, around the arbitrary value to the left and right hand side. So it means that we have 4 different possible, I would say, outcomes, right?
Okay, yeah.
For example, graph could look like this, or like that, or like this, or again from the other side. These are basic pattern that you're gonna define all the time.
Okay.
And also remember, by knowing that the function travels to, for example, positive infinity to the right hand side, from this asymptote. Remember, because limit is distance very close to the point. So we can state that if it's gonna be in positive infinity right next to the point, then it's gonna decrease farther away from this asymptote.
Okay, yeah.
Okay, perfect. So,
I'm just gonna go to the bathroom really quickly.
okay, let's make a 10 minutes break, okay?
Okay,
And then we're gonna continue.
okay.
Perfect. Are you back, guys?
I'm back.
I.
Okay, just a second. Let's continue. And we're gonna start with simple exercise. So Yusuf, I would like you to work on example A. So
Okay.
state the equations of the vertical and horizontal asymptotes of the curves shown.
Okay.
So let's discuss the graph A. First of all, can you state the vertical and horizontal asymptotes?
The vertical asymptote is 2. And the 2
And
and -2.
can you be more clear? What is 2? What is -2?
The asymptote is for the vertical is 2. So you see here, the graph never touches 2. So that's the asymptote. It reaches 2, but then it never touches 2. That's the vertical asymptote. And the horizontal is the horizontal asymptote is 1. Because we see here,
He means with the equation, like x or y equals.
what do you mean? Like,
Yeah, so basically we were asked to state the equation of these asymptotes, and you define those asymptotes absolutely right, like how function behaves around those points, etc. But in order to, for example, tell next person who's gonna read this graph after you, what vertical or horizontal asymptotes you have to state their equations. And in this case, for example, vertical asymptotes are gonna be located for 2 values of x, right?
yeah,
Let me change my pen color. 2 values of x. And what are those values?
2 values of 2 and -2.
Absolutely right. So we have 2 vertical asymptotes. One of them x equals 2, and the other one is x equals -2. Am I right?
Yeah.
Yeah.
So basically this is equation of our vertical asymptotes. Because remember, how would you plot this graph? X equals 2. This is it. This is
Yeah.
just going to be x equals 2.
Yeah, they're in the
Vertical
middle.
line, right?
Yeah.
And what about horizontal asymptotes? If I say horizontal,
You can say like just like you said, y equals 1
now exactly. For horizontal asymptotes, we would say y equals.
equals 1. Yeah.
And now y equals 1. This is exactly gonna be the limit of
The
our
limit.
function as x tends to be positive infinity, right? Here
Yeah.
is gonna be positive infinity and negative infinity. So these are three actual equations because we have 3 asymptotes, 2 of them are vertical and 1 horizontal. Now, Alan, can we discuss graph B with you?
Yeah.
So let's go start with vertical asymptotes.
Vertical asymptote is x equals 0.
Okay.
And I don't think, no, it's not, I don't think, there's no horizontal asymptote on this one.
Could be 4, I think.
The only problem is the arrow, it's pointing down, so it means it continues down.
Oh yeah.
So in this case, we actually gonna have vertical asymptotes x equals 0. You're right. It's gonna be right here. Because you see to the left and right hand side from this point, y limit of this function, or basically y, you're gonna be traveling to either positive infinity or negative infinity to the left and right hand side, right?
Yeah.
Another thing that we don't have any other vertical asymptotes right here. That should be clear based on the visual observation. We see that we have two critical points. However, those are not horizontal asymptotes because remember definition of the asymptote?
No point cross the crossover.
Yes, no intersection.
Yeah.
And thus, we gotta look for other horizontal line, and I see this y equals 0 horizontal asymptote. Because as you can see, as x tends to positive infinity, y is limited to 0, and as x tends to negative infinity, we're gonna have the same limit of a function, y equals 0.
Cross is at 1.
Pardon?
Cross is at x equals 1 and -1. Yeah, there.
Good. So what can we say about this horizontal line? Is it actually asymptote?
No.
It's not an asymptote for whole graph, but
Oh,
it's gonna be local. It's
it's
gonna
a
be asymptote for certain interval, for example.
horizontal asymptote and limits at infinity.
Pardon?
Is it like the limits at infinity asymptote?
Basically, what we're gonna see here that after this point, if we look at the point in the specific interval, for example, from 1 to positive infinity, we're gonna see that in this range, in fact, we have horizontal asymptote.
Yeah.
But Alan is completely right. We cannot say that this is horizontal asymptote for the graph because this graph is passing this line.
Passing it, yeah, it's going over.
So we have only one vertical asymptote that is clearly visible.
Okay.
So can I clear the drawing now?
Yeah.
Let's move on to the next exercise. And now we're going to evaluate limits for following functions. And before we start that, I would like to ask you guys, do you remember one cool property of polynomial functions? That the greatest factor, the greatest power in the function, in polynomial function, is also can be a factor of this polynomial function.
Yeah.
So we can factorize any polynomial function by coefficient with the greatest exponent.
Isn't it that if the denominator has a higher power than the denominator, then the horizontal asymptote is 0. And then
If denominator is going to be a greater power.
yeah, it's
If after simplifying the function, it turns out that we are dividing by 0 or dividing by positive or negative infinity,
Yeah.
we're gonna have limit equals 0. Thus, it's gonna be horizontal asymptote 0.
Oh, okay, yeah.
And if it's if they're equal, then there's no horizontal asymptote, or then there's none.
Sorry, I didn't understand.
If the power is equal in the denominator and denominator, then there is no horizontal asymptote.
We still have to examine it. We still have to examine the function and see what result it's gonna give us.
Okay.
Because let's solve A, for example. You said that if nominator and denominator has the same power, then we're not gonna have any asymptote. So this is exactly example as you said, right?
Mhm.
Two polynomial functions of the same power, and we need to find limit for them as x tends to positive infinity and x tends to negative infinity. So let's do it. What would be a first step, guys? Say we know its limit as x tends to infinity, an equation of 2x plus 3 over x subtract 1. If you go ahead and substitute x for infinity here, you're gonna have a problem. Infinity divided by infinity, which cannot be solved, right? So there's one step we need to perform before substituting x for infinity.
I don't know.
What I just told you about before this exercise, remember the property of polynomial functions that we can factorize them.
Yeah, but I can't see anything we could factorize.
I cannot agree with you because why can I divide this by x? Why can't I divide the numerator or denominator by x? I can, and I'm gonna show you how it looks. If I factorize it by x, right?
Yeah.
I'm gonna have 2 plus 3 divided by x,
Okay.
3 divided by x. Isn't that what I'm getting?
Over what?
Over x. Here we are factorizing by x, so we have 1.
Subtract.
Subtract 1 over x.
Yeah.
And now we simplify it. We have common factor x. And we have 2 plus 3 over x over 1 subtract 1 over x. And now we're going to substitute x for plus or minus infinity, right? So let me substitute for positive infinity. I'm gonna have 2 plus 3 over x, whereas 3 over x turns into 0, right? Because 3 over infinity is 3 divided by super big number, basically 0. Am I right?
Yeah.
Mhm.
So I have 2 plus 0. In the denominator, I have 1 subtract 1 over x. If I substitute x for positive infinity, I'm gonna have positive number here, right? So positive number really small, close to 0. So 0, basically.
Yeah.
So one subtract 0. Simple step, 2 over 1. And it turns out that the limit as x travels to positive infinity gonna be 2. If you substitute x for negative infinity, you're gonna see that you have exactly the same thing. but only the sign would be a little bit different. You're gonna have 2 subtract 0 because x is negative number, and we divide positive number by negative, we're getting basically -1, but still it's close to 0, so we don't care about the sign in this case, right? Here it would be 1 plus 0, which results in 2 over 1 or 2. Is it clear?
Yeah.
I'm just I'm writing it down and see if I have any problems.
So basically we evaluated the limit, even though we had a problem at the beginning, but by factorizing the polynomial function, we got rid of that problem and evaluated the limit. So if I were to plot this graph, what horizontal asymptote would it be?
Horizontal?
Yes, absolutely, because remember, horizontal asymptotes are happening when x tends to infinity.
Yeah.
So it would be.
That's why we have this exercise. This exercise basically shows us how to look for horizontal asymptotes.
So it would be. Wait, so for this step here, did you just sub in negative, the infinity?
Yes, for this one, I substituted x for infinity.
Doesn't matter which one, negative or positive.
As you can see in this case, if we divide by infinity, basically it doesn't matter, because if you divide any constant number by infinity, it's gonna result in 0. It's gonna be a really small number close to 0 from either positive or negative side. So we really don't care about its sign because it's so small.
Okay, and any number divided by infinity is 0.
Any constant
Constant.
divided by infinity equals 0.
Okay.
Or equivalent to 0 would be a more correct way to say it, because we cannot divide by infinity because it's not a number.
Hmm.
Remember, infinity is only a symbol that describes how function acts there. And thus,
What does the 2 equal?
pardon?
What does the 2 equal?
2 is a limit, it's L. 2 equals L, limit of a function,
Okay.
as L tends to positive infinity, and here this would be also L, but as x tends to negative infinity.
Okay.
As we see in this case, limit is the same.
Okay.
Let me know once you're done. So where would be this horizontal asymptote? Guys?
It would be
Would it be a 2?
Yeah, y equals 2.
That's how you find the horizontal asymptote.
Yes.
And vertical asymptote is just that would be 3, so 1/2.
Vertical asymptote in this case would be x equals 1. Because this is the point where our function is undefined.
Well, I thought, isn't the vertical asymptote the denominator?
Pardon?
Isn't the vertical asymptote denominator?
I don't really understand what
Oh,
you're
I, th-
trying to say.
I thought the vertical asymptote was what x equals in the denominator.
Uh, not when nominator equals 0, you mean, right? What x equals
Yeah,
in nominator when nominator
yeah.
equals 0. That's you're confusing it with first derivative test. That's
Oh,
where it is. In first derivative test, when function equals 0, we have critical point.
mhm,
Remember?
yeah.
When derivative equals 0. And derivative equals 0 when its nominator equals 0. But
Okay.
for vertical and horizontal asymptotes, we have another property. Basically, for horizontal asymptotes that x should tend to be positive or negative infinity. And for vertical asymptotes, we're looking for y to travel to, so limit to be positive or negative infinity, and x could be any constant.
Okay.
And y would be infinity for rational functions like this one you see when denominator equals 0.
Okay.
So how can I clear that board?
Yeah.
So let's do C now. Alan, can you please draw on a board right here and solve C for us?
I'll try.
Using the same method, please explain it.
Okay. So we could. Can we factor out an x? Oh, we could factor out x from the top, not the bottom. What if we divide? Um, hmm. Let's try this. Um, Over here, I just factored out an x in the top.
Remember that for polynomial functions, factor could be coefficient with greatest power. As we did in previous example, we factorized by x to the first power because it was the greatest power. Here we have x to the zeroth power in front of constant. And in example C, we have x squared.
Oh, okay. So I factor out x squared. But then how would you factor out an x squared from 3x?
As well as we did in previous example. You basically divide
Oh, okay.
by a missing term, by missing coefficient. Because x times 3 over x is equivalent to 3. Am
Yeah.
I right?
Yeah.
So you can do that.
Over here, I just factored out the same thing in the denominator.
No worries.
Now you could factor, cancel out these.
Yeah,
Let's,
don't forget to write what you're doing. Right now you're in the process of finding the limit as x tends to be plus or minus infinity of this function, right?
yeah, sorry.
Because now you're going to substitute x for infinity and you would like to be accurate.
So for this one, it's x squared. So even if you put a negative infinity, it's always going to be 0.
Yes, of course. Because remember, when you divide any constant by 0, you're getting 0 as an output.
Mm.
So the limit for this function would be
You could simplify it to negative 2.5.
great.
Oh, so in school, they taught us that to find the horizontal asymptote, you look at the coefficient of the first term of each, and that's how you find it. You divide them.
Yes, basically what they're not saying to you
That's
that there is a
mathematical.
missing step in between where you're factorizing those polynomial functions. And that's how you're getting rid of this axis in front of your coefficients. And then you divide coefficients.
Okay.
And basically now you proved that you're looking on coefficients in front of the greatest power. Because all the rest of the terms are turning into 0 when you're factorizing it and sticking the limiting value.
Okay.
Does it make sense?
Yeah.
Because for any term that has a variable with not the greatest power, is going to be divided by this variable at the end of the day, right? And it's
Mhm.
going to be divided by infinity because we're looking for vertical asymptotes. Oh, horizontal asymptotes, sorry.
Mhm.
Clear?
Yeah.
So now let's do example D. Yusuf, would you mind trying?
Yeah, sure. For D, just
So you don't need to copy this equation again, just write the first step right after. D, limit a function as x tends to plus or minus infinity. This equation, and how would you factorize it in order to solve?
so first thing I would do, factorize it is um wait, first thing to evaluate the limits, right? Or like factorize it first and then
So let's factorize it and then see what we get.
Okay,
Don't be scared of equation. It should be scared of you. Just split it up in pieces, cut out all unnecessary stuff, and you're gonna find the answer pretty easily. Just follow the guidelines, factorize it, and
so
don't think
factorize
twice.
it, so
Do you want to draw or you want me to write?
I'll write, yeah. So to factorize,
So remember that the factor is gonna be the greatest power of the
yeah,
polynomial function.
so it'd be 2x 5.
You don't need to copy it again.
No, not copying it, just like, oh, actually, oh yeah.
So whenever you factorize the equation, are you factoring the highest power on both sides, or like, so like for example, like would you factor the x 5 the x to the
No,
power of
I'm gonna factor uh for
So in
x.
you're factoring by the greatest power of specific polynomial function. Because,
Okay,
for example, in this case, if you factorize both numerator and denominator by x to the fifth power,
Yeah.
here it will result in 0,
all zeros. Okay, so it'll be of the
So the
all
greatest,
zeros, and you cannot divide by 0, remember?
yeah.
yeah,
Because you're gonna have problems such as but actually here you can, guys, here you can, because you won't have any problem for this particular case. And you're gonna see why for this case, it doesn't matter whether you factorize by x to the fifth power or x to the fourth power,
So
because
because
limit is going to be the same in both cases.
okay,
oh, okay, yeah.
In another example, if you factorize by for example, by such a power, and you're getting 0 on top and on the bottom, for example, or infinity on top and 0 on the bottom, you have a problem.
so you could factor out a x to the 5 power on both top and bottom,
Yes, you can do that.
but not for all.
For this particular case, it works,
Okay.
but again, here you can factorize by x to the fifth power because we have polynomial with the greatest power of 5 on top, and it's gonna be our factor in this case.
Okay.
And I can't come up with example when it wouldn't work right now, but that's why we have theorems and algorithms, because you know, theorem is correct unless it's proven to be wrong.
Mhm.
For maybe you're gonna see example of equation when you're doing that and you're getting a problem. If you do it in another way, you won't get a problem. But for this particular level of equation, you can like fairly simple factorize both numerator and denominator by x to the fifth power.
Yeah.
So Yusuf, can I give you a hand?
So what I'm gonna do, I'm gonna factorize. I already factorized it, but I'm gonna simplify it right now. So it's gonna be this divided by
Unfortunately, Yusuf, I don't really understand how you end up with this, because if you factorize it as I suggested by x to the fifth power,
yeah,
you simply bring it out of the brackets and write 2 subtract 3 over x to third power
yeah.
plus 5 over x to fifth power divided
Oh,
by
okay, yeah.
x to the fifth power
The power, yeah.
3 over x subtract plus 5 over x to the fourth power subtract 4 over x to the fifth power. Now you simplify it,
Simplify, yeah.
and next step you see that this turns into 0, this turns into 0, as well as all of the terms in the denominator. And we end up with 2 divided by 0.
Which equals undefined or none.
In another case, it would be correct, but we are dealing with limit function. Remember, guys? And
Mhm.
with limits, everything is possible. With limits, in this case, when denominator equals 0, after substituting the value of x, limit would be equal to infinity. Read the description. Evaluate limits as x tends to infinity using the symbol infinity when appropriate.
Okay.
And this is a case when limit equals 0 equals infinity.
Okay.
And remember, it means that we have basically what this says as x travels to infinity, or x infinitely growing or infinitely decreasing, y would travel to infinity as well. So basically, even this graph, which is just a line at an angle of 45 degrees, also satisfies this limit, because when x infinity for such line, y is also infinity. Am I correct?
Yeah, that
Mm.
makes sense.
So in this case, we don't have horizontal asymptote. Do you understand it?
Yeah.
Because in all other examples, we discovered that limit equals some arbitrary value, right? Some constant value. And that was our horizontal asymptote. But in this case, we found out that no limit, no specific limit exists in this point when x travels to infinity.
Okay.
And do you understand now why it doesn't matter if we divide by x to the fifth power or to the fourth power? Because if you do the same stuff and you factorize top by x to the fifth power and bottom by x to the fourth power, do you see that on top you're gonna still have coefficient x, right? Because you had x to the fifth power divided by x to the fourth power. And this will result in denominator equals infinity. Am I correct?
Yeah.
Because if we substitute x for infinity in this case, we would have numerator equals infinity, and the denominator would be some arbitrary value, or in this case, it would be 3. Make sense?
Yeah.
So, and infinity divided by 3 is still infinity. Thus, the limit would be the same. So you can say that limit equals infinity if either numerator equals infinity and denominator is a constant, or if denominator equals 0 and numerator is constant. Any questions, guys?
Nope.
No.
Okay. Let's move on to the next example, and it's going to be final example for us today. So for each of the following, check for discontinuities and state the equation of any vertical asymptotes. Conduct a limit test to determine the behavior of the curve on either side of the asymptote. So, Alan.
Yep.
Why wouldn't you solve A for us?
Okay. Check for discontinuity.
Now, which one should I solve?
No, it's for me. Okay, so
A.
okay, we're trying to find the vertical asymptote. Can you remind me what the discontinue?
No, discontinuity is when function does not exist
Okay.
at a point. So check for discontinuities. Basically, so find when function is undefined.
Okay. I'll try. So the vertical asymptote would be x equals -5.
Okay.
And the discontinuity would be, would it be x equals 0?
So actually discontinuity would be at x equals -5.
Oh, and the vertical asymptote would be at x equals 0.
No. Remember, vertical asymptote is when x travels to some constant from plus or minus, right?
Mhm.
It's a limit. And whereas of f of x, and this limit should be equal to either positive or negative infinity. Remember 4 cases that we discovered. When we have vertical asymptote, we can do like this, or like that, or like this, or like that. Make sense?
Yeah.
So, and what happening with the limit of a function around this asymptote? Y travels to negative infinity in this case, and to positive infinity on the opposite side. Make sense?
Mhm.
Yeah.
And that's what exactly what you see here. So basically, discontinuity also may identify a vertical asymptote, but not always, of course. For this case, to test for vertical asymptote, you would find the limit of this function as x travels to -5, right? If you
Mhm.
substitute x equals -5 in here, you're gonna result in constant divided by 0, which gives us infinity.
Okay.
Now, you gotta test it for left and right hand side. Conduct the limit test to determine the behavior of the curve on either side of the asymptote.
Okay.
What is the limit test? When x approaches this some constant value from the left, and the second case when it approaches it from the right hand side, right?
Yeah.
So first test is gonna give us what is the limit when x travels to -5 from left hand side. We would
Yeah.
state this equation, and we're gonna see that if we approach it from the left hand side, we're gonna have negative number on top, or negative 5 explicitly, right? Except for x, instead of x.
So you get negative infinity.
Wait, let's see. On the bottom, I'm gonna have number that's slightly less than negative 5, which is negative 5.1, for example. Am I right?
Yeah,
So it's going to be negative 5.1. So negative 5.1 plus 5, how much is that?
0.1.
Negative,
Negative 0.1, sorry.
because we are approaching negative 5 from left-hand side. Is it right? So let's start plotting this on our graph.
So you got positive.
So I got negative 5 here. I have vertical asymptote here. And as I approach it from the left-hand side, I'm going to have values such as negative 6, negative 7. Am I correct?
Yep.
So from positive side, I have slightly more negative power or negative value. So slightly more negative than 5 is going to be slightly more negative than 5 plus 5 is still negative, right? So I'm going to have negative divided by a really small negative number, basically, or you can say negative 0, which is going to result in positive infinity.
Okay.
Remember how we identify the sign of a function when we have multiple products or even divide? We'll look into the sign of each product term, right? And see what would this operation give us at the output. For example, here we have two negative numbers, which results in positive number because we're dividing. So now, second example, when x travels to 5 from negative side or from the right, we would have slightly more positive numbers than negative 5 or negative 4.9, for an instance. Am I correct? So we're going to have negative number on top divided by positive number, which will result in negative infinity. Is it clear?
Yeah.
yeah,
So from the right-hand side, our graph would look like this, right?
yeah,
And from the left-hand side, it would look like this. Is it clear?
Yeah.
So what would be the equation of vertical asymptote for example A?
It would be -5.
So x equals -5. And how function behaves on either side of the asymptote.
It would be positive on the left and right, negative on the right.
So I would say that my function is
Or
increasing. First of all, I would say that my function is increasing to the left-hand side from this asymptote to the positive infinity.
it's also increasing on the right.
Absolutely right. But it's
It's not-
increasing from negative infinity. It starts increasing from negative infinity, basically.
Yeah.
On the other hand, if we had something like this, we would say that it decreases to the right-hand side.
Yeah.
And we also identified direction at which function goes to the left and right-hand side, basically. Direction towards positive infinity, on the other side from negative infinity. So is this example clear?
Yeah.
Can I clear the desk now?
Yeah.
Yusuf?
yeah, I got it.
Perfect. So Yusuf, do you feel confident about trying to solve?
B.
Would you like to try B?
Yeah, so first to check for discontinuities, we need to look for any values of x that make the denominator of the like function equal to 0 or equal to 0. So for this one, we need to, the denominator is -2. So the function will be discontinuous at x equals 2.
Absolutely right. So x equals 2, we found the point.
Yeah, and to determine if there's any vertical asymptotes at x equals 2, we can do the limit test. So when we can approach x equals 2 from both like the left and the right. From from the left to see if the function approaches infinity or negative infinity. So from the left side of x equals 2, we can approach with the values x less than 2. So so limit fx as like x approaches 2 to negative equals limits wait, can I write it on the board? Because I have it written on
Yes,
paper.
of course. I've wrote something here for you.
Yeah,
So this is where you ended, that we can approach x
yeah, as
from.
x approaches 2 equals negative infinity. So from the right side of the x equals 2, we can approach with values greater than x. With values greater of x um greater than 2. And what's left? Let's see. Well, since the limits from both sides approach infinity, we can conclude that there is a vertical asymptote at x equals 2. So that's the vertical asymptote.
Beautiful.
Yeah.
And what about behavior of the curve on either side?
Behavior of the curve is um like to determine the behavior of the curve.
Look
we
at
can
the
just-
sign of the infinity that y is traveling to.
It's negative
On one side and on the
and
other
positive
side.
on the other side. Yeah.
So can you plot shape of a graph based on vertical asymptote you found and on the sign?
Yeah. So
You can use this to sketch it.
um so wait, I'm actually not sure how to like sketch it exactly.
So start with vertical asymptotes. You know that vertical asymptotes at x equals 2. And you
Yeah.
know what is the sign to the left-hand side and right-hand side from this asymptote.
Yeah. So we know that the vertical asymptote is at x equals 2, where the curve approaches positive infinity. And as x approaches 2 from the left, the curve would have like I'm not sure how to exactly like word it.
So what I see here that my limit is going to be negative infinity when I'm traveling to 2 from the left-hand side. So it's going to be bottom, right? Negative infinity is here because this is +1, this is -1, right?
Yeah.
Negative infinity on the bottom. So My function approaches negative infinity when it comes close to the vertical asymptote from left-hand side. So it's gonna look like this, looking down, right, to the
Yeah.
negative infinity. On the other hand, from positive side, what would happen, Yusuf?
The positive side, since it would go like that. I'm not sure how to explain it, but
Yeah, so if you look here, you're gonna have numbers slightly more than 2, right?
yeah,
So you're gonna have slightly more than 2 subtract 2, which results in positive number.
yeah.
And slightly more than 2 plus 2 is also positive number.
Also
So we're gonna
positive.
have positive divided by very small positive number, or almost 0, which results in positive infinity. So
Positive.
to the right-hand side, it would be here. Positive infinity is here,
Yeah.
right? So it's gonna look like this. So can you state whether function increasing or decreasing to the left or right-hand side?
The function is increasing to the left. Or wait, it increases.
They're both decreasing.
Oh yeah, they're both decreasing.
Here to the right-hand side, actually, if you see, for example, if you keep substituting x for values greater and greater than
Yeah,
2, you're gonna see that in fact this function would keep growing,
yeah, it increases to the left.
but still you have a problem that it's actually not growing, because look what's happening here. In the in the denominator, you have number that is basically more than x, right? So it's
Yeah,
numerator in this case greater than denominator. So we're gonna have number different greater than 1. Am I right?
yeah,
But you can see that as you making x bigger and bigger, difference between numerator and denominator like decreases, because if, for example, x equals 1, we're gonna have 3 divided by negative 1. Then if x equals, for example, 3, we're gonna have 5 divided by 1. But then x equals 6, and we already have 8 divided by 4, which is 1 over 2, or 2 over 4, or 2 over 1. And this is less than we had one step before. Remember, when we have 3, we have 5 over 1. When we have 6, we already have 8 over 4. And 8 over 4 is less than 5 over 1. Am I right?
yeah,
So basically, function is going to decrease.
Hmm.
If you substitute x for million, you're going to have million and 2, right? And here you have 9,999,998, right?
yeah,
And this number is not much different from 1, right? So it means it's getting even smaller, because it was 5, then it was 2, then it almost 1 once we go to million. So actually what I see here, that I'm also gonna have kinda maybe horizontal asymptote later.
yeah.
And what would it be? I
Uh,
already see it.
The horizontal asymptote?
Yeah, you see, as the greater x turns, the closer I'm getting to certain value. So limit, I'm approaching limit of my function. And what would be the limit of this function if x travels to positive or negative infinity? It's question for both of you guys.
2
Almost.
-2.
So you see here, I substituted x for million,
Mhm.
and I almost reached 1. If you see that you keep increasing x, it's gonna get closer and closer to 1. In fact, you can test it by solving limit of this function. Limit as x travels to positive or negative infinity. Remember horizontal asymptotes, how we check for them. X travels to infinity, right?
Yeah.
So I'm gonna have x plus 2 over x minus 2. And next step is to factorize it. X, so 1 plus 2 over x divided by x, 1 minus 2 over x, right? Simplifying, turning this into 0, and I'm left behind with 1 over 1. And that's my limit. That's my horizontal asymptote.
Okay.
Isn't it fascinating, guys?
Yeah.
So basically, I'm gonna have another horizontal asymptote y equals 1 here. And thus, now I already can plot my function almost with 0% mistake, because I know that my function is decreasing on both sides, right? And I know that I have vertical asymptote and horizontal asymptote. So my function would start from positive infinity to the right-hand side and try to reach this horizontal asymptote, right? To the left-hand side, it would start from negative infinity and also try to approach this asymptote. And this is actually an example of what we started at the beginning of the class, but with vertical and horizontal displacement, isn't it? Remember, let me move back in our course. Here, no, not here, but this one. Do you see it? Let me
Yeah.
move this. Do you see? Exactly the same graph. Compare it, isn't it? The same two two branches, isn't it, guys?
Yeah.
Same one horizontal and one vertical asymptote, isn't it?
Yeah.
Isn't it the same? Alan?
Yeah.
So now, guys, I hope you strengthen your understanding in this topic. And thank you for participating in today's class. This was the last exercise for us today.
Thank you.
If you have any questions, please feel free to email me, and have a beautiful evening, guys.
Right. Thank you.
Good luck.
Have a good day. Bye.
You too, bye.